Hi everyone, welcome back. Welcome to our online lecture notes. Today we're going to be thinking about a question that we've thought about before, how we can add up information. We thought about this in some other contexts before, and so here we're going to be bumping up the dimension and thinking about how we can add up information for something three-dimensional. All right, and so just to get us there, let's get there step by step and think about what this looks like in lower dimensions. So in dimension one, if we have something one-dimensional, like say this interval from A to B, when we might have some information about each point on this interval. So at this x, we have some info there. That information we can write as a function, right? F of x we can think of as our information that we have at x. And so attached to this x, we can stand up maybe like a little stick attached to that interval. And if we go through and stand up these sticks, each x in our interval, right, then what we actually get is the graph of our function. And what's going to go through and add up all that information is an integral. Right, so the integral for f of x from a to b, this is going to go ahead and add this up, and it's going to give us area, right, or more precisely, net area. Let me write that in here, net area. And so we've seen that before, and more recently, we've thought about what this looks like in dimension two. Right, so here if we have something two-dimensional, like a chunk of the xy plane, we can imagine having information at each point on this plane. Maybe this is some sort of thin plate, and we're taking temperature readings at each point in the plane. Right, and so at each point xy, we have some information, and we can think of it as a function value, and whatever that is, we can say stand up a stick with that height. Let's say that the info at this point was like 5, then this stick would have height 5. All right, and if we go ahead and do that and stand up all these sticks over every single point in this region R, then again, what we'll be constructing here is the graph of our function f of xy. And here, if we go through and use a double integral, we'll add all of this up, and that will give us volume in this case, right? The volume bounded there. So that gives us net volume, but I'll just write volume. All right, so stepping this up a dimension, in dimension 3, we now have a three-dimensional thing that we have information about, right? So here we have some solid brick, right? So the idea here is that this B is solid. That's a D. So as in filled in, right? It just gets kind of weird if you try and shade everything. So this kind of brick here, or if you want to think of it as some piece of jello, it's all filled in. Right? And at each point in this solid brick, we have some information. And again, we could think of this as maybe we have a chunk of the Earth and we're taking temperature readings at each point in this three-dimensional chunk. But the issue here is that we can't draw the graph anymore, right? If we try and like reach inside this this brick, we try and stand up some sort of green stick, we don't really have a direction to point it that doesn't jam into the brick, right? We don't have this third direction fourth direction to draw in, and so we can't draw the graph anymore, which might make us a little bit sad, but it's also kind of cool. So that's nice. But anyway, the idea here, if we go through this solid brick and add up all this information, well, what's going to do that is this object over here we call a triple integral. And this thing is going to go add this up, And right, so what's it going to give us? Well, geometrically, right, dimension one, we got area. Dimension 2, our double integrals gave us volume. Dimension 3, we're going to get the next dimension up. What do we call that? We just call it hypervolume for like 4-dimensional space. I'll write that in here. Gives hypervolume. All right, so kind of hard to see, but that's the idea. Somehow some 4-dimensional space is what we're getting from this triple integral. Okay? And today what we're going to do is kind of try and get our bearings with this idea and then work through an example. And to start getting our bearings, one of the nice things is that thinking by analogy is very useful and just works beautifully for the ideas here in this dimension that kind of maybe pushes us outside of our comfort zone. And so let's see a few examples of how that looks, how analogy plays in. So first of all, one of the things we've seen, if we're doing a double integral and we are integrating over the constant function 1, that's just going to take our region and puff it up by 1, and this will end up, the double integral would end up giving us the area of the region. Well, here, with a triple integral, if we take our brick and integrate the constant function 1 over it, that's just going to take it and somehow puff it up by 1, and the triple integral is just going to hand us actually the volume of that 3-dimensional region B that we were integrating over. All right, so this formula, when we're integrating the constant function, generalizes beautifully. We also have a nice generalization with our average value of a function. Right, for double integrals, it was 1 over the area of our region times the double integral. Here, right, this next dimension up, we have 1 over the volume of our blob times the triple integral is giving us the average value of our function over that 3-dimensional region B. All right. Also, thinking about integration, right? dA in rectangular just broke up as dx dy or dy dx, whatever order we were thinking about that in. For dv, the idea here is that we just have 3-dimensional boxes instead of 2-dimensional kind of rectangles. And so here, if we start from a point, move out by dx and dy and dz, we get this kind of box thing. And the volume is what is dv, right? In this case, it's just a box. And so dx, dy, dz gives us dv. Right, but similar to double integrals, again, we have choices, right, of how we want to integrate. With double integrals, we could do dx, dy, or dy, dx. Here, we have more choices, actually. We could put dy up front, dx in the middle. We could switch the dy or the dz, or we could switch the dx and the dz. There's actually there's 6 possible choices for integrating, which is nice. We like choices, but also can feel overwhelming. You know, what do I do? Well, we'll talk about that. And before we get to kind of how to choose a nice order, let me first say that the instructions that we get from a particular choice of order are completely in analogy with what we've seen with double integrals. And so the instructions from the variable order, once we've chosen that, we're going to take our inside-most variable first, moving that, holding the others constant. Then work our way outward, move our second, holding the third constant, and then finally move our third. And this second and third movement that happens over B's shadow. This might seem like new territory, but I claim that it's actually stuff we've seen before, at least by analogy. So let me try and convince you that this is all in nice analogy with what we've seen before. Okay, so over here on the left, we have a picture of a region that we might be integrating over for a function of two variables, right? We got some r, and we want to integrate over it, right? And we could possibly think about, what order to do it in, but it doesn't take too long to see that, well, if we set y, move x, things are just going to be horrible. And we're going to need multiple integrals, and it's going to be really icky. But if we instead, set x and move y, then we're always starting at this bottom curve and stopping at this top curve, right, for any of the x's between 1 and 4, right? And so here we just need to kind of give some names to these curves if we're going to write up our limits. And so here on the bottom, let's say that this is given by some y equals a of x, and up top, if y equals b of x. And again, the idea is that no matter what x we pick, we get consistent instructions, right? As we move y, we're starting y at the bottom curve and ending it at the top as we move in the positive direction, right? So we get these consistent instructions, and because of that consistency, well, down here we can write our limits of integration, right? As we set x and move y, we're always moving y from our bottom curve, a of x, to our top curve, b of x. And our limits for x, right? These answer the question, well, what x's do we do this for? And right, we're doing that from x equals 1 to 4. And what I claim is that these limits from 1 to 4, these really we can think of as coming from the fact that if we take our region here in the plane and we look at its shadow on the x-axis, right, kind of take its y direction shadow, well, then what we get is the interval from 1 to 4. Right? That's the shadow that we get. And so these outside limits just tell us to move across that shadow, starting from x equals 1, then moving to x equals 4, to move all the way across that shadow. Okay, so now let's bump up the dimension, and over here have a, sorry, get the right color. Now we have a three-dimensional kind of wedge shape, just kind of floating in space here. And now we're imagining that we have some function of 3 variables that we are integrating over this thing. And so let's imagine, first of all, moving our z variable, holding x and y constant. Right? So for moving z, we want to imagine just like lying down on the xy plane here and just looking straight up at our wedge here, and I don't know, blowing a spit wad up through this wedge, okay? And so as that spit wad comes up, right, we're moving z, and notice we're gonna start hitting our wedge at this kind of bottom side here, and we're gonna move up and then pop out of the top at this kind of slanted side there, right, as we move z. And now if we pick a different spot over here, maybe like this spot, and we again, kind of come up in the z direction, if we move z, then we're going to start z at this bottom side, and we're going to move on up and then pop out of the top at this slanted side. And so hopefully we can see that this is going to be consistent, right? No matter where we start kind of underneath our wedge here, we're always going to start Z at this bottom side and end Z at the top. And that's going to move us through. And so because of those consistent instructions, we can use those sides as our limits for our first integral as we're moving our Z variable. And so we're going to get moving Z first, so dz is the inside. And so we just need to give some names to this stuff. So this bottom side is going to be some function Z equals a of xy. And this top side, right, that's going to be the graph of some other function, say b of xy. And so down here, for our limits of integration for z, right, these are telling us as we move z, we're always going to start at our a of xy side, and we're going to stop at our b of xy side. And now the question is, what xy points do we do this for? Right? What xy points are going to be underneath this wedge that as we move up, we're actually going to move through this solid here? And the answer is, well, they're the xy points in the shadow of this thing. Right? And so here we've taken the z direction shadow, kind of imagine having a flashlight up here. Oops, there it is. That's a flashlight. Shining down on this thing, just perfectly flat on either side. This thing projects down and gives us this sort of region R as a shadow. And so that's what we'd want to move y and x over is that shadow. And so here I'll just write dy dx, just to pick some order to move across that shadow. And so here, again, R is B's shadow in the kind of Z direction. So maybe I should say kind of B's Z shadow, since we moved the variable Z first. All right, and so the idea here is very much in analogy with what we've seen before. I'm moving our first variable, holding the others constant, and then moving the others across the shadow of that thing in the appropriate direction. So, so this is kind of the picture, this is the idea. And what I'd like to do now is look at how this can play out with a particular example. Okay, so here we go. You gotta kind of be choosy about what functions we're using. We're gonna let things be computable. So here, this humble little x, this is our function of 3 variables, x, y, and z, that we're integrating over some solid blob b. And this solid b, we're told here, is bounded by the paraboloid, by this equation, and the plane x equals 4. Okay. And so, if we're going to start cranking through our integrals here, which we'll have 3 to do, in order to get started, we need to figure out our limits of integration. And as always, to find these, we need a picture, right? In order to think through our start-stop instructions and now what the shadow looks like and all of that, how to get a hold of it. So we want to draw a picture for sure to get started. And so here to think about this paraboloid. If this was, say, like z equals with x squared and y squared, that would be opening in the z direction. The positive z direction here with x equals this stuff. this is going to be opening in the positive x direction, and then we're just going to cut things at the plane x equals 4. So putting that together, we get a picture that looks like this. And so here's the paraboloid over on the side. And here, we've kind of cut that thing off with the plane at x equals 4. And I did not label my x-axis. I apologize. Okay. And so we kind of have this solid filled in thing. It's like some sort of like Christmas ham, right? That is our three-dimensional region that we are going through and adding up this information with our triple integral. Okay. And so we need to think about, okay, do I want to think about moving x, y, or z first? And here a kind of a hint is given, our kind of boundary are given as, x equals something. And so let's maybe think about moving x first. That might be a clean way to think about things. And so the question is, as we move x, do we get consistent start-stop instructions moving through our Christmas ham? And so here the idea is, right, so if we're moving in the x direction, we want to imagine maybe like backing up against the yz plane, and moving in the x direction, we're just moving kind of just purely in the positive x direction, and we're going to start, blink, right when we hit our ham. We're going to keep moving in the x direction until pop, we come out on the x equals 4 side there, right, moving that way. And so the question is, well, does this always happen? Well, let's maybe pick a different starting point behind here. If we maybe start here and move in the x direction, we're going to blink, come in at the paraboloid, and then move through in the x direction, and then pop out on the x equals 4 side. And I think because of the symmetry of what's going on, hopefully it's reasonable that yes, we're going to consistently start at our paraboloid and stop at our plane as we move in the x direction. And so here, this is a big check. We do have consistent instructions, and because of that, we can use these sides as the limits of integration for our insidemost integral, and we're going to move x as our first one, and we'll figure out what to do after that. So dx is going to be our first. Okay, and so starting to set that up. We've put the equation for our paraboloid here, right? That's our starting instruction, and we're stopping at the plane x equals 4. And right, we're moving x first. We have dx, and then dA is for our second and third variables, which we are going to now move over r, where r is the shadow of our Christmas ham in the x direction, right? So now we gotta imagine we have like some magical flashlight over here, right? And we press the button and turn it on, and what does this Christmas ham give as its shadow? Well, the fattest kind of edge of the ham is right here at the x equals 4 kind of disk that we get defined here. And so, right, the kind of the picture here is, if we kind of bring that back, the shadow we're going to get is going to look something like that, right? And so here, that's going to be our shadow in the YZ planes. It's going to look something like that. And so this is kind of the visual of what it looks like, but how do we actually, figure out, what's the equation for the outside edge of this thing? Well, we can use the geometry of how we got it, right? Well, we said that this thing came from essentially this rim of the paraboloid that we got by cutting with x equals 4. In other words, this outside edge is coming from the x equals 4 trace of our paraboloid. And so we just need to figure out what that trace is at x equals 4 for our paraboloid. That will give us the outside edge for our region. And so to figure out the trace at x equals 4, right, we just need to take the 4 and pop it in for the variable there. All right, I'll scroll the rest of the way down. Okay, so here we go. Here we have our paraboloid equation here, and we popped in the 4 for x to find that x equals 4 trace. And so this is going to give us some curve in the yz plane. And just by dividing by 4, we can see, oh, this is the nice unit circle in the yz plane. All right, so here is that edge that we drew up above. And we just know that we also want all the stuff inside of it because that's part of the shadow that our Christmas ham leaves in the YZ plane. Okay, and so we just now need to figure out how to describe this thing, right? We technically could use rectangular coordinates. We could think about setting y at something, say, and moving z from the bottom half of this circle up to the top for all the y's between -1 and 1, right? And so we'd get these limits, these instructions for moving z and then moving y. All right, but that doesn't sound so nice, right? This is a circle and polar coordinates, right? That's going to be a much cleaner way to think about describing our shadow here because it's a disk, right? And so the description in polar, right, for any theta we might want to choose, right, there's a theta. We want to start r at 0 to get the origin and then move on out up to r equals 1, right, the outer radius of that circle. And we want to do that for all the thetas from 0 to 2 pi in order to get the full circle. So here's our nice description of our region. And here on the right, I've just recorded here our translation equations for using polar. Notice in the YZ plane, right? So here in the YZ plane, our Y is our horizontal axis. So that Y becomes our cosine theta, since it's the horizontal. And Z is the vertical axis. And so that becomes our sine theta. And we have our Pythagorean theorem identity. Y squared plus Z squared equals R squared. And dA, as always, becomes r d theta. All right, and so we'll use these to help us set up the rest of the integral. So let's go ahead and fill in the rest of our limits of integration and also work with our dA here and using what we found about the shadow here. Okay, so moving on down. So to start, this is the same inside integral as before, but now we have our r and theta integrals as always. We want our theta to be on the very outside, do that one last. So r is moving from 0 to 1, theta from 0 to 2 pi. And here, notice I've taken the dA, which we know is r dr d theta. And we could technically leave it like that, but here I've taken the liberty of taking this r, and it just looks a little bit cleaner if we kind of slide it in. It's a constant with respect to x, and so I've just kind of slid it in next to the x there. All right. And so at this point, things are looking pretty good. We have all of our limits of integration. The only thing that we could possibly take issue with is looking over here on the right the d's tell us what our variables are, right? So here, x, r, and theta are our variables. And if we look throughout our integral, we actually see some other stuff showing up. We still have some y's and z's going on. And so what we need to do is just translate this. That says translate. And so here, y and z, the yz plane, right, we used polar to describe that, and so we can use our translation equations up here. We could technically swap in r cosine theta, r sine theta, but that's not going to be as clean as possible. If you look here, you might have seen kind of what's going to be nicer way to think about this. We can pull out that 4, yeah? So here, if we pull out that 4, y squared plus z squared, and this boils down immediately to 4r squared. And with that translation, everything is all in terms of our 3 variables, x, r, and theta. Everything's fully translated. We have all of our limits of integration. Life is good. And all we have to do now is work through 3 integrals, starting from the inside and then working out. All right, but the idea here is, as we've seen before with double integrals perfectly in analogy, and so here the idea for our first integral is that r and theta are constant and x is our variable, and so we want to integrate xr with respect to x, right? R is just some constant multiple here, and so we're just really integrating the x. It's going to be x squared over 2. I'll just bring up the rest of it. So that integrating the x gives x squared over 2, and we want to evaluate that from x equals the 4r squared up to 4. And so we'll just one at a time, right? Plop these in. So plopping in the 4, we get 4 squared over 2 times r. Subtract what we get when we plug in our 4r squared, which is 4r squared over 2 times r. Right? And so we can do a little bit better here. And simplify this. So over on the left, 4 squared is 16. So over 2, this is going to be 8r. Oh, I just realized something. I was planning on taking this. I was planning on taking this over 2 and pulling it out real clean as a 1/2. But I forgot to adjust what I had inside, and so scratch that. And if you were confused about that, then good job. That shouldn't be there. Okay, here we go. So yeah, ignore that. And now with the plugging in the 4, we get what's on the left. Plugging in 4r squared, we get what's on the right. And we'll just simplify where we are. What are we going to get? So again, this is going to be 16 r to the 4th times r, and so we'll get 16 over 2, again that's 8, and we get r to the 4th times r, which is r to the 5th. All right, and so we could either leave it like that, or we could pull out that common factor of 8 all the way out front. Either way, at this point we now just have a double integral to compute. And so we can work through, the first integral with respect to r, evaluate, and then when the dust settles, integrate with respect to theta, evaluate. And I encourage you to work through the rest of that. Just over here, what you'll end up with is 16 pi over 3. That is the hypervolume that our triple integral is giving us, moving through our Christmas ham, adding up our function information there. Maybe just for our notes' sake, I'll just add here. So now now it's a double integral, and we can go ahead and compute it. All right, that's it for today. If you have any questions on the lecture, post those to Piazza, and I'll see you next time.